Moin, me again, Mark Albrecht. Thanks for watching the third part of creating an environment-aware animation rig in Houdini or elsewhere, because I'm still hoping that you can transfer whatever I'm talking about here into something else. This third part will concentrate on the rigging and hooking up the system that we created before. In the end, I'll leave it up to you to optimize the animation parameters, but I will talk about possible extensions or enhancements to the scripts. Right, with that said, let's have a look at this beautiful spider model, the tarantula, I'd say, that David Mars has created for this tutorial. Thanks, David. You can see from the reference grid that this spider has been living on a power plant. It's huge. The model comes in as one geometry, so I'll start by creating some primitive groups that will allow me to hide the body, because I want to start by concentrating on the legs and hooking up the animation system to them. I want to make sure that I include everything in the body group that I don't want to rig with the animation system, so I'm including the eyes, parts of the mouth and the backside into the body group. Then when I hook up a visibility node, I can switch on and off the body just as I need it. I like to have my rigs separate from the geometry, so I create a subnetwork and call it rigs, couldn't resist, and then only do the linking by the deformation system. Laying out the bones is pretty simple. Click on the rigging shelf and then on bones. Use some sensible naming for the chain, like L for left or R for right, and leg or whatever you want to rig, and then add a number, because if you later on use copy and paste, the numbering will take care of correct naming, and if you use a prefix like L, you can use the mirror tool to spare you half of the work. You could of course use divisions to get all the in-between bones laid out in one click and then adjust positions, which I have to do anyway. I'm adding the inverse kinematic solver right away, and I use the view-based positioning for starters, which will try to place the bone ends or the bone controls somewhere suitable on the geometry. This doesn't always work perfectly, so I have to do adjustment by hand. So I switch over to freehand and then do a little bit of cleanup on the positions. I'd say this is looking good enough so far. We may have to do some tweaking later on, but let's have a look at what we got. The goal will be what we will be controlling by our animation system later on, and the kin chops subnetwork is where the inverse kinematic solver is being stored in. If you decide to add your inverse kinematics or whatever later on, that will create such a subnetwork. You can of course extend the kinematics by adding a twist node and then simply linking that one into the solver. Depending on how you laid out the bone chain, you may have to tweak the twist factor a bit. I was going to say you have to twist the tweak factor. I think I need to do something else. For now, I'll leave the twisting out and just go with the standard inverse kinematics. Don't you worry, you don't have to watch me doing the other legs manually. I'm simply adding another one by hand, because the pedipalps have one joint less than the walking legs, and then I do copy and paste, which may involve a bit of renaming action, but practicing typing is a very good preparation for the retirement hobby plans. Don't forget to at least check the kinematic solvers. Sometimes the links get updated correctly, but sometimes they don't. There's no need to be surprised if your spider blows up in a weird way. After copying and pasting the bones, you of course have to manually adjust the positions. For that, it's a good idea to hide the bones that you have been copying, so you have access to only the pasted bones. Try to place the bones approximately in the center of their respective geometry. That will help the capturing or skinning process later on to find the optimal points for the weighting. Once you have done one side of the rig, and assuming that your model is somewhere around symmetrical around one axis, you can use the mirror tool to get the other side of the rig working. In the version of Houdini I was using for this part of the video, there were some minor bugs, so I had to cut out the rig from the subnetwork, paste it in the top level hierarchy, and do the mirroring there, else I would get some weird nodes that I really didn't want. Anyway, this problem is solved. If you have a recent daily build or whatever installed, you don't have to worry about that. You can leave the nodes, you can leave the bones in the subnetwork and do the mirroring there. With that said, you could skip ahead now if you wanted, but if you're interested in problem solving, then just continue watching. We got some warnings here, and the warnings point out that, like I said before, sometimes the links don't get updated correctly. So always have a check if you see some warning somewhere. Also, the kinematic solvers would need updating, but we don't have to worry about that because we're going to put all the bones back into the subnetwork later on anyway. The mirroring tool still has some bumps in the version I'm using right now. In general, select all the nodes that you want to mirror, then go to the modify shelf and choose the mirror tool. Give the newly created nodes a new prefix. In my case, it's R for the right-hand side. And in the next text field, you define where the first stop for the replacement of the prefix is. So if you named your nodes L underscore whatever, then the stop sign would be the first underscore. After you set up the mirroring correctly, press enter over the viewport to start the actual mirroring. Quick tip or workaround note. Side effects helped me figuring out that if you do it the way I did, and that is first select the nodes you want to mirror, then start the mirroring tools, you may get some buggish looking results. It's better to start the mirror tool and then select the nodes you want to mirror. If you did it the way I did, first select the nodes, then start the tool, you may get some unwanted results. Like, for example, I have to fix all the IK solvers now. They didn't get mirrored. If you did it the other way around, first start the tool, then select the nodes, then execute the tool, the newly created IK solvers for the mirrored side, in this case for the right legs, will be put in the IK solver subnets of the left-hand side. The IK solver subnet for leg 1 will, after the mirroring, contain both the IK solver for the left-hand side leg and the right-hand side leg number 1. Like I mentioned, the version I was using here had some small bugs, so I have to do some manual cleanup, which mainly involved creating or recreating the IK solvers and making sure that in the first bone the links to the IK solver were fixed as well as the IK solver naming. Again, it's very probable that you don't have to go through all this. Side effects fully agreed that these hiccups are not necessary, and the more recent versions of Houdini already had huge improvements on mirroring bone networks. One way or another, it's always a good idea to check what an automatic tool has done. Almost finished. I'm leaving these parts in because I want to show that sometimes you don't have to worry for hours where you went wrong, like I did. Sometimes it's really just the tool that had a bad day, and then it makes sense to just take a couple of minutes to fix up the mess instead of trying to figure out where your head and the wall had an encounter of the smashing kind. Right, now we got what people sometimes call the skeleton laid out, and we also checked that all the inverse kinematics are working properly. The next step is to capture or skin the geometry to the bones. And Houdini offers several methods. I'm not going through all of them step by step, but I will show you the few that you'll probably use the most. We'll start with biharmonic capturing, which is a new capturing method introduced in Houdini 16, giving you almost perfect results on many meshes. The overall workflow for the process is the same for all capturing methods. I'm adding a single dummy placeholder node for the body, since we left out the body rig for the moment, and then I connect all the leg root nodes, parenting them to this body node. We need that in order to allow the capturing process to have a single root from which to crawl down the legs. If we didn't have that connecting root node, we would have to create individual rigs for every single leg. With the root node available, we can start the capturing process by going into the rigging shelf and selecting capturing geometry. select the biharmonic capturing type, and then first select the geometry if you don't have that selected already. And after that, select the body placeholder node, which acts as the root node of the skeleton now. Once the capturing process is done, you should check if the deformation is working correctly. It looks almost perfect on the pedipalp, but we get some very minor deformation on the roots of the walking legs. But we get some stronger interaction, we can see it here, on the legs. That shouldn't be a problem because in the end these parts will most likely be hidden underneath the body, but we can fix it anyway. Just to demonstrate what happens if we reactivate the body or make it visible again, you can see that the body points have been weighted all along, so we get some weird and probably quite unwanted deformation, like the mouth parts are being moved along with the pedipalps. No, we don't want that. For the moment, for the sake of having a look at the other capturing methods, we change the body grouping here that we created for the visibility flag from primitives to points. That allows us to ignore the point group body down in the capturing process. And in Houdini, you put an exclamation mark before the group name to tell Houdini, do not use this group. If the recapturing doesn't start automatically, triggered by the change you made further up the line, you have to restash the cache node. And that simply means invalidate the cache that you created for the capturing. That will force Houdini to redo the capturing process from start. No more not so funny deformation on the body, but on the downside we don't have the body following along the rest of the rig. The second way of capturing the geometry is the kind of classical way of using the existing capturing regions or C regions on the bones. Every bone, when you create it, has a C region, and that region can be used and even modified to define where on the geometry the points are being automatically selected for that bone. Of course, this method has disadvantages and advantages. A disadvantage would be that the shape of the capturing region is very limited, as you can see. An advantage is that on very repetitive or very simple geometry, this might actually be the fastest way to capture what you need. Again, we need a common root node that we're going to parent the leg roots to. By choosing C regions as the capturing type, we get ourselves in a somewhat workable starting situation. It doesn't look too good, but keep in mind, C regions works for any kind of geometry, not just closed watertight geometry. And you can get somewhere by selecting all the nodes and carefully adjusting the C region parameters. In this case, with the partially overlapping or at least quite close geometry, C regions isn't the most flexible way. So let's have a look at the third method, which is proximity capturing, that can provide you with almost the same quality results as biharmonic capturing, but obviously depends on carefully placed bones, as proximity means capture on the nearest points, obviously. Deformation doesn't look too bad, but of course we do get some unwanted overlap deformation where the geometry is quite tight. There's no way around manually correcting the weight maps now, and one way to do that is use the capture paint node. The place where you want to plug in your capture paint node is after the initial capturing has been done, but if you have a cache node, before the cache node obviously, and definitely before the deformation node. If you do have a cache node after the painting node, then make sure to put the visibility or activity flag, the blue flag, on the painting node, not on the deformation node, because otherwise your painting may re-trigger a cache stashing or re-evaluation of the rig, making things very slow. The Capture Paint tool is really powerful. On first sight it looks quite simple. Like the description says, you select a bone which weights you want to modify, and then you define what your left mouse button is to do, like paint weights, and what your right or middle mouse button is to do, like soften the weights or whatever. Hold down Ctrl and press the middle mouse button to select the currently active bone that you want to paint for. And you see on the top of the viewport or in your parameter window which bone you currently have selected. Make sure this field isn't empty, because otherwise you'd be painting on some default weight map, and since Houdini is kind of auto-normalizing weights, that may or may not influence all your other weight maps, which can, take this from first-hand experience, definitely unmake your day. Anyway, trying to hand paint a model that has overlapping geometry with points penetrating polygon groups is somewhat with P. Possible? No, painful. Painful is the word. I'm lucky, however, that this model comes with point groups or polygon groups, which means that each part of the leg, each joint, is its own separate connected group of points. So when I'm in point selection mode, press 2 on the viewport, I can use connected 3D geometry. This mode also gets activated by pressing 9 on the viewport window, and then a little info pops up in the upper right corner showing you which connected 3D group you're currently hovering over. That helps enormously with getting the painting done. Use the New Group arrow top right in the parameter window, or hover over the viewport and press N like New Group to select the currently active restriction group. And then you either press somewhere outside the model to have no group selected, or you select one of the connected geometry groups, and then your painting will be restricted to only the group that you have selected. This way it's easy to avoid unwanted stray strokes. With this specific model, with the spider, I actually want to bind all the points in one leg joint 100% to the respective bone. The painting tool has some tricks to do this. First, I use Ctrl middle mouse button to select the bone for which I want to modify the weight map. Then I use N or the group arrow to select no group whatsoever by clicking somewhere outside the model. With painting opacity set to 1, I did this earlier, I use whatever button I have assigned to reduce weight once and then click on Apply to All. This deletes out the complete weight map for my selected bone, so I have a blank slate to start from. Then I can use the group selection tool to select the correct joint and do a single paint stroke, again opacity set to 1, and again Apply to All. By this I'm setting all the points in my selected joint to full weight, and I don't have any overlapping between this joint and the next. While I'm now going through all the legs cleaning up the weights, you can either have a cookie or coffee, or I'll pause the video and we see each other after I had one. Welcome back if anyone should have been gone. We still need to get the body geometry into our rig, so let's tackle this. The most simple way, which of course we won't go, is to create a secondary rig, weight the body geometry to the secondary rig by restricting the point group to body only, and finally parenting both rigs to a common master root. But I promise not to go the simple way, else the video would have been done by now and could have been uploaded 2 weeks ago. The body skeleton will be oversimplified, just using 2 single bones for the body parts and 2 separate bones for the mouth parts. Feel free to go overboard with the complexity if you want to. Let's parent the mouth parts to the body parts so that they interact correctly. Move it up to where we need it, and then hold down the Y key to cut out all the connections from the placeholder. Move the body rig in place and connect it up. The leg roots all want to be parented to the second body part. because that's where they are hooked in reality. Let's have a quick check if we wired it all up correctly. Yep, that looks like spider yoga. If for whatever reason we want to be able to find the nodes later on by using a search function, some renaming makes sense. Like I said before, one way to deal with the body now would be to create a secondary weight map for just the body bones, separate from the other root, and then hook them up or wire them into the common root after we got the weights working. But that would mean that every time we want to change something in the weighting, we would have to separate the rigs again. So instead, I'm going to get the body worked into our existing weight map. The polygon group or primitive group was only useful for the visibility flag, and we don't need that anymore. Instead, we're going to create a couple of point groups, but first let's restash the cache. I think there's a song in that. Okay, the body has been included in the weight maps. This is looking good enough. However, trying to move the second body part only, this is definitely not the capturing or the weighting that we want. In case you don't believe that, try to move a leg and you see the body is getting chewing gummed. If we have a look at the mouth bone here, we can actually see that it doesn't have any weight at all. It seems like we have to check where the capturing process is looking for bones. I am now using the biharmonic captured spider, which isn't in any way animal unfriendly. Therefore, the responsible node for which bones are to be respected on the capturing process is this one, called Edgar the Responsible. No, actually capture lines. We have to add the Edgar bones, the edit bones, into the selection mask of the capture line node. Hold down the control key and then select just the bones, not the root or anything else. This entitles you, after another stashing of the cache, to a better weighted rig. Obviously, better isn't perfect. This is way too organic. Is there a thing like over organic? I need another cookie. Right, let's deal with the overlap in the weighting. Unfortunately, the body isn't created in separate chunks, so we have to create a couple of point groups if we want to use the capture paint node's clean tag. We could, of course, hand paint everything, but I tried it and it's rather cumbersome. And since we only have a very simplistic rig with a couple of bones only, we really don't need that much of organic deformation. First, let's hide out the legs. So we need a polygon or primitive selection group. Then I can go on separating the body into elements that I want to be able to deform independently. The connecting area between the two body parts is tricky in this model. I can go in and manually select all points that belong to each distinctive body part, but there's another way, and I'm going to show you. If I have a group that contains all groups in the body, I can weight that complete group first and then subtract those body parts that I do not want for each bone. Nah, I didn't understand that either. Don't worry. Let me just demonstrate what I mean. Actually, there's another workflow that you can use, and that's again using the visibility node. You can make Houdini convert your point selection for body part 2 into a virtual primitive selection group, and simply hide that. And by that you get a perfect or accurate separation of the two body parts. Well, at least as accurate as the point selection drawing was. With that, we should be good to go and use the Capture Paint node extensively. I did say so before, but I like repeating myself. Did you notice? Set the activity or visibility flag to the painting node, not to the deformation node. Otherwise, we will constantly re-trigger evaluation of the complete capture process, and that is not what you want. I have shown the overall workflow before, which involves selecting the bone that you want to weight, then first clear out all the weights for this specific bone by selecting No Point Selection Group. Click on Reduce Weight with opacity set to 1 and then Apply to All. Then select the group in the geometry, the point group that you want to weight to this bone. Press on Paint and Apply to All, and that will give you a full weight for that bone. Obviously, if you want to, you can smooth out the areas in between. I am also going to check the first bones on the legs so that I don't get too much deformation happening from one leg to the next. And there's some red shining through on the body, so there's quite a lot to do here. Always have a test run in between. For that, set the visibility flag back to the deformation and then check all the legs and check everything to see if there is some unwanted deformation going on. However, due to the way Houdini has been distributing the weights over all of the geometry, you may miss some stray values even if you look very closely and even if you check all the neighboring bones and just can't find any spots. Like if you have a look here, the front legs, the pitfalls, are still deforming the mouth areas, even if I can't find any stray values responsible for that. You can spot part of the problem by realizing that some of the first bone areas on the legs aren't really 100% weighted, which means we may have to clean out more than we expected to. A side thought, there is a node called Capture Override, and that allows you to use a spreadsheet kind of interface to really control which points get which weight. Personally, although I can do with spreadsheets, I find it hard to use, so I'll stick with the Capture Paint node and solve all the troubles bit by bit. Right, another cleanup round. The problem I'm still facing is that I can't figure out where the stray deformation for the mouth parts is coming from. What I'm going to do is I'll redo the body weighting here. Like I said before, if you have no bone selected, in theory there shouldn't be any color, any weighting visible on the model. My assumption is that you sometimes see some math inaccuracies here or whatever. Looking at the first bones of the legs, I can see that there's some weighting blowing over into the body, and I think that's causing the trouble on the mouth area and probably elsewhere. What I'm going to do is I'll one by one select the first leg bone and then clear out the weighting on the point selection groups for all body parts. By that I should get rid of all stray weighting from the legs. While we're at it, why not do the same for the second and third leg bone as well? Let's see if that did it. Not totally. There may be still values on the legs because I did clean out the maps on the mouth area for the legs, but I did not clean out the maps for the mouth area on the legs. So let's do that. Select the mouth bone, or actually make sure that nothing else has some stray values. Again, select the mouth bone and as the point selection, select whatever part of the leg is causing the trouble here. Then clear out that map or clear out those point values. That seems to have done it. Thanks for watching. No, not yet done. Hang on. I can't let you go without actually plugging in our MCP system. I put the MCP from the experimental rig into the clipboard so that I can paste it in here. And now I have to wire it up to our new overall scene file. The solver node is quite modestly unhappy because in there, I think we did just about everything wrong. We don't have a world, we don't have a rest position, and we probably have to fix the attribute wrangle just as well. I think we don't even have animation parameters yet. While I'm mentally preparing to do everything from scratch again, let me have a word about the rest positions. In theory, we could just as well create the rest positions for the feet from the root position of the body and the zeroed out goal positions of the feet, and just do that on the fly within the code. But that would mean that we can't really adjust the rest positions if we need so for the animation, because the rest position would be kind of hard-coded by the geometry. And now, honestly, come on, Mark. Copying and pasting the goal nodes to some rest nodes, zeroing out the transforms and renaming them.
Even you lazy German can do that.
Does Cookie get out of her studio? And just to annoy that guy, I'm not going to copy and paste the goal nodes, but create a new rest node. Whatever. It isn't really necessary to clean out the transform or translate channels, but that helps if you later on want to animate the rest positions, which makes sense if you want to better react on environment or give the Spidey some individuality. With that done, it's time to add a world. For the demo videos, I imported some 3D scans I quickly made on the field behind our house, but I think for this completion here, another sculpted grid may do. Note that for whatever unknown reason, I'm creating a subnet, and in that subnet I'm creating a geometry which is another kind of a subnet, and inside that subnet, inside the subnet, I'm creating the actual geometry. Yes, I did lose myself there as well, and yes, it's going to create a minor problem. And yes, I'm only doing this to extend the length of this video. No, I'm not. Finally, trying to sculpt out the spider from the ground reminds me of the vast hugeness of this specimen. That should do it. Let's get back to the solver and get the worldwide into this object. The root node we luckily already have, so we can simply select it from the drop-down. Just make sure that relative path is active if you want to copy and paste the MCP afterwards, else you would have to correct the root node path every time. The rest position, now that we have it, should work just as well. What is Houdini trying to tell me with this? Object world is not correct. Let's see. I want it to be there. Now root is wrong with the same problem. And if I reselect, what is going on? Okay, let's ignore it for the moment. Time to deal with the code, or actually create the parameter list, I'd say. I'm way too old and too puzzled to remember the parameter names. So let's add a floating window and use that to open up the parameter editor. I'm going to put the parameters into the main rig node. While this, of course, isn't as flexible as having parameters on each leg individually to allow for various leg stretch thresholds, it's a bit easier to wire things up in a single MCP and use copy and paste. For a highly configurable version of this rig, you may want to choose to put the parameters on each leg or give the afterthoughts a go that I'm going to add. Well, with the folder for animation parameters created, let's add in all the floats and the ramp that we need. And hopefully I get the naming correct. That would make the interface look complete so far. We can adjust the paths in the code. And since I'm using the rig, which is right now on the top hierarchy, finding the path is quite simple. Again, if you want to create a more flexible version, you'd probably have to do some relative path counting here. This isn't our only MCP, this is MCP1. And of course, we have to wire in the output, the foot position from MCP, into the goal of the inverse kinematic solver for each leg. Hang on, is it foot push or is it foot position? I think it's foot position. Yep. Right, we're getting some output here. So let's have a look what the visuals are saying. Houston, we got animation, but we lost ground control, as it seems. This isn't just bottomless, the leg is also overstretched, so the rest position is incorrect. It's not completely incorrect, but it's too incorrect. I have selected the goal because that is what we are influencing from our script. And the goal value for x is saying 0 point something and z is 1 point something, but we are on 3 something. So obviously we have some garbage in the pre-transform, which we can simply reset out. As a reminder why this works, resetting the pre-transform, we are actually setting the world position of the goal from the script. Adding some blind positions to that just doesn't make sense. We are doing our calculations in world space already. With stretching solved, let's check why the intersect with the world isn't working. As I pointed out before, I created a subnet, and in that subnet I created the geometry net. So what we do want to access isn't the geometry out from the subnet, but the actual out from the sculpt. With this corrected, we now get an impatient Spidey. Whoops, that's a new one. That's mainly a scaling issue. The default values I put in the parameters are depending on the experimental rig, but this spider is huge, so we need to pump up the volume. I played around with the values trying to find an optimum maximum distance, but it's quite impossible, and the reason for that is the front legs are rather short, so the standard distance, default distance between rest position and root is a lot shorter than with the hind legs. I'm going to deal with that problem in a moment, but another thing I notice is that the front legs aren't moving at all. Spidey isn't just impatient with me, Spidey's actually tired of me. Since the front legs can't be overstretched right now, it must be the minimum distance that should trigger the motion. So let's have a check if we set up the parameters correctly. And no, the minimum distance has a typo. It should be min distance. Now Spidey is still tired, but at least it looks healthy when she's got a breakdown. Before I'm going to mess with the max distance issue, I just have to get rid of the stray weight values. That is driving me nuts. I hope you can forgive me that I did this in offline mode. So one idea about the rest positions is that they are quite far from the body. It might make sense to move the rest positions closer to the body and maybe a bit forward. This is actually something that you have to experiment with. It really depends on the type of spider or type of insect or whatever you're using, and definitely will also depend on the surrounding and the environment. To me, this is already looking a lot better. It may not be the most realistic walk cycle yet, but honestly, if we wanted realism, we would do it in camera and not in post. Spidey is moving like a spaceship. We need a ground scanner to have the body react on the ground height. We are currently animating the old body placeholder root, which is fine because then we can use the root of the body bone skeleton to plug in the Y value, the height offset from the ground scanner. All we need is a point to wrangle on and a wrangle that we are going to point to. And then we do the old-fashioned intersect ground scanner magic. This time, just for a change, I'm not going to read out the parameters from the transform, but instead I'm going to import the control node and just pipe that one into the second input of my wrangle node. That spares me a couple of keystrokes. I also need the collision geometry or the intersection geometry, and that is the world. This time I'm not falling for the geo out. I have to clean that up, but I'm using the sculpt output. If you'd like an in-depth explanation of the intersect function, please have a look at the first video in the series, or for a short recap at the second video. For now, let's just pretend that you know what I'm doing. That would make one of us. We are checking for intersections both downwards from the control node and upwards, and that's for a simple reason. In the experimental rig, I made sure that the path I lay out is above the ground. But you never know what an animator comes up with, so it might be that the path is going through the ground somewhere, or that the path has been laid out and then somebody decides to change the terrain. In short, it's better to check for all improbabilities. With the ground scanner code in place, we can use the point position result and drive the Y channel of the body root. Since the rest of the body, including all of the leg rigs, is parented to the body root, that will be sufficient to keep Spidey above the ground. Right, but where's Spidey? In this case, we are simply completely uncooked. So either we resim or we just rewind to 0 and start a playback. And there's Spidey. We definitely need to give her some headroom, or is it Tommy room? With Spidey so well fed and huge, and the ground quite unpredictable, why not add another parameter to control the height above ground? Because parameters can be animated and are much easier to control than having to dig into some channel expression stiff stuff. Simply rig the reference into the Y channel, and now we got a controllable Y offset for Spidey. Time for some test animations. I will speed up the video here quite a bit, because in the end I have to admit that we still have to change something. The problem being, while I do get animations as such, I just can't control the max distance threshold well enough. And I talked about that before. The front legs have a very short distance from root to goal or rest position, while the hind legs have a very long way. The distance calculation root of leg to foot position just isn't going to work for this specific model. One way to solve this would be, of course, to have separate parameters on each leg. So the hind legs could have longer maximum distances and the front legs shorter. But how could I call myself a problem solver if I didn't constantly create problems for myself? So instead of doing it the right way and having parameters for each leg individually, let's change the code and the way we're calculating the current distance. What we've been doing so far is that we check the current foot position in world space against the root position of the leg in world space. But with the legs having so very much different length, this calls for individual rigs or MCPs on the legs. But we do have some kind of constant distance. And that is, once the foot or the leg is stretched, we're moving towards the rest position. So the constant is rest position versus stretched position. Ergo, we can simply exchange the root position with rest position for the distance calculation. That will give us a constant threshold for a stretched leg, because the end position for the foot is always the rest position. Either we change all the codes manually, or we just copy everything over to all the other MCPs, and by using the URL or the address line in text mode, we can get there quite quickly. Let's give it another try. and the experimental values are completely bogus. Getting there, and I like to repeat myself, you have to experiment with parameters. There is no silver bullet. It depends on the overall scale of the scene. It depends on the ground. You have to play around. But after all, this is a lot faster than hand animating all the feet. Playing this back in real time doesn't look too bad actually. And we see one problem that's quite obvious. We have most of the legs on both sides up in the air at the same time, and the rhythm on both sides is the same. Like I said before, it might be a good solution to have each leg individually rigged with animation parameters, but a completely different idea would be to not have single MCPs per leg, but to have one overall global MCP. If you allow me to get back to the beginning of this all and do another scribble for ideas, then it could look like this. One idea would be to have one MCP node, and inside that node have one point per leg that you want to animate. The advantage of this would be that you could use threading parallel execution of the wrangle node. In this scenario, you would use the attributes on each leg point, so to say, so each leg could read out the foot position from its respective owning, wrangle point, if you want to call it that way. A completely different approach would be to have a global number of legs, a global parameter in the rig node that defines how many legs are being used in the MCP. So the MCP would have a for loop inside that would iterate over the number of legs and output an array of foot positions that the legs could read out. The advantage here would be that you don't have to create points for each leg, but you would simply define an overall global number of legs. So the whole rig could be used for a centipede, 1,000 peed, whatever peed. However, what I'm targeting is the idea that if you have a single MCP, a single control program, that would allow you to have a global parameter of how many legs are currently up in the air, meaning how many legs are in anim state 1. That's quite difficult to achieve with the individual MCP rigs, but it's very easy using a detail attribute on a common geometry. And once you got some global information about how many feet are in the air, you could orchestrate feet to work in pairs like they do on real-world spiders. A lot of ideas come to mind if you have control over which foot is currently where inside the MCP that's doing all the control. On a completely different line of thoughts, you could check the average Y position of the front feet and compare those to the average Y position of the hind legs, and by that get an angle that the body should be pointing upwards or downwards in. That would allow you to tilt Spidey's body, or maybe even only its body part 2, into the direction it's climbing, up or down. That, of course, triggers the next idea of storing the direction the body is currently moving in. So that would allow you to rotate body part 2 or probably body part 1 into the curve that the spider is walking, making it slightly lean into its track. Or instead of using geometry nodes for all the MCP stuff, you could use chops. Or you could do it completely different. Or, well, I just shut up now. Thanks for watching.